before proceeding to use phasors to analyze circuits driven by sinusoidal sources, we should check and make sure that our circuit analysis techniques are valid in the phasor domain. Fortunately, all the circuit analysis techniques we've learned are based on Kirchhoff's two laws, KVL and KCL. The only exception to this is superposition, which applies to any linear circuit or any linear system and linear operations. And the phasor transformation is a linear operation, so we know that superposition already applies. Consequently, if we can show that Kirchhoff's voltage laws and Kirchhoff's current laws apply in the phasor domain, then all of the other circuit analysis techniques that we develop from them will also apply. So we'll start by taking a look at Kirchhoff's voltage law in the phasor domain. Kirchhoff's voltage law tells us that the sum of the voltages around the loop, V1 plus V2 plus all the way down to Vn, must add to 0. Well, if I can have any voltage, then each of these voltages can be cosine functions, so I can replace them with the amplitude of our first cosine function, V1 cos omega t, plus the angle of this voltage, plus I can have an amplitude of a second cosine function, which again will be operating at a particular frequency, and it will also have its own angle, plus all the way down to the last voltage, which will have an amplitude Vn, and it will be cosine omega t plus its angle n, and that must add to 0. Now we've put in all signals at the same frequency, which is what we need to do for phasor analysis. I can shift and scale this. I can scale by the imaginary constant j, and if I shift them by 90 degrees, the cosine becomes a sine function. And I will end up with V1 sine omega t plus, I'll have the same angle. I've added 90 degrees, but I've taken that up by converting it into a sine function. For the next term, I'll have j with an amplitude V2 sine omega t plus, again, the same angle as before, plus all the way down to j Vn sine omega t plus the angle n will equal 0. I can add these two terms together and use Euler's form to express the equation as V1 e to the j omega t e to the j angle 1 plus V2 e to the j omega t e to the j angle 2 plus all the way down to Vn e to the j omega t e to the j angle for the nth term should all add to 0. Now when we go to the phasor domain, we suppress the e to the j omega term, but you can also see that it's a common factor in every one of these, so I can simply cancel it out, and I will be left with, putting this in phasor form, magnitude V1 at angle 1 plus the magnitude of V2 at angle 2 plus all the way down to magnitude n at angle n will be equal to 0. And we can see that the phasor form satisfies Kirchhoff's voltage laws. More importantly, you'll notice that what we have here is a vector sum, and the vector sum must add to 0. So in the phasor domain, Kirchhoff's voltage law can be expressed as a vector sum of voltages around the loop that must add to 0. We could do a similar procedure for Kirchhoff's current law, where we'll start with simply currents that become cosines, convert them to sines, and multiply by the imaginary number j. We can convert that to Euler's form. We'll go through exactly the same procedure, and we will find that the vector sum of the currents at a node must also add to 0. So Kirchhoff's voltage laws and Kirchhoff's current laws apply in the phasor domain. This is excellent news because it means every circuit analysis technique that we've learned up until now we can use directly in the Phasor domain. Before proceeding to do that though, we'll take a look at how we can transform the circuits themselves into the Phasor domain.